Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. The limitations of classical computation became apparent not through failure, but through the growing recognition of problems that resisted solution despite endless processing power. Some calculations scaled poorly, their difficulty growing exponentially with the size of the problem. Doubling the input didn't double the computation time. It squared it or cubed it, or worse. For certain classes of problems, adding a single additional variable could multiply the required computation by factors that made the difference between seconds and centuries. Cryptography relied on this computational asymmetry. Creating a coded message using two large prime numbers was trivial. Reversing the process, factoring the product back into its prime components, was brutally difficult for numbers of sufficient size. The security of encrypted communications rested on the assumption that no amount of classical computing power could factor these numbers in reasonable time. As commerce and communication moved into digital channels, the integrity of this assumption became increasingly critical. Chemical simulations faced similar walls. A molecule's behavior emerged from quantum interactions between its constituent atoms, electrons sharing and exchanging energy in ways that classical physics couldn't adequately describe. Simulating even a modest molecule required tracking countless quantum states, their superpositions and entanglements, their evolution over time. The computational requirements grew so rapidly with molecular size that simulating useful chemical reactions remained beyond reach, forcing researchers to rely on approximations that sacrificed accuracy for tractability. Optimization problems proliferated across logistics, manufacturing, finance, and resource allocation. Finding the absolute best solution among astronomical numbers of possibilities demanded evaluating combinations that exceeded the atoms in the universe. A traveling salesperson visiting just 50 cities could choose routes numbering in the tens of digits. Classical computers could find good solutions through clever algorithms, but proving those solutions were optimal, or even finding truly optimal solutions for complex scenarios, remained computationally intractable. The physics community confronted their own computational barriers when modeling quantum systems. Understanding superconductivity, designing new materials with specific electronic properties, predicting the behavior of exotic states of matter. These required simulating quantum mechanics, which meant tracking probability amplitudes for every possible state a system could occupy. The number of states grew exponentially with the number of particles, quickly overwhelming any classical computer's ability to store even the description of the system, let alone simulate its evolution. Material science needed to predict how atoms would arrange themselves into crystal structures, how defects would propagate through solids, how interfaces between different materials would behave at atomic scales. These were quantum phenomena, governed by wave functions and probability distributions, by tunneling and superposition. Classical simulations could approximate some behaviors, but missed the quantum effects that often determine the most interesting properties. Drug discovery relied on understanding how molecules would interact with biological targets, how potential medications would bind to proteins, whether they would produce desired therapeutic effects or unwanted side effects. This was molecular simulation at its most complex, requiring accuracy about quantum interactions in systems with thousands of atoms. The computational cost forced researchers to test compounds physically, a slow and expensive processor of trial and error, guided by intuition more than precise prediction. The common thread through these diverse challenges was their quantum nature. They were problems rooted in the behavior of nature at scales where quantum mechanics governed, where particles existed in superpositions of states, where measurement changed what was being measured, where entanglement created correlations that classical physics couldn't explain. Trying to simulate quantum systems on classical computers was like trying to describe a sphere using only straight lines, possible in approximation, fundamentally limited by the mismatch between the problem's nature and the tool's capabilities. The recognition spread through scientific communities that certain problems weren't just hard for current computers, but were fundamentally mismatched to classical computation. No amount of faster processors, larger memories, or cleverer algorithms would render them tractable. What was needed wasn't more of the same, but something categorically different. A computational substrate that operated according to quantum rules, that could represent superpositions natively, that could exploit entanglement rather than fighting against it. The exponential scaling that made certain problems intractable had a deeper implication. Throwing more classical hardware at them didn't help in any meaningful sense. If a problem required examining 2 to the power of the number of variables, then doubling your computing power simply allowed you to handle 1 additional variable. The gap between what you could solve and what you needed to solve didn't shrink. It remained exponentially large, merely shifted slightly. This stood in stark contrast to most engineering challenges, where sufficient resources could overcome obstacles. Building a bridge across a wider river cost more, but was fundamentally the same problem. Transmitting data across longer distances required more signal strength, but used the same physics. But simulating a quantum system twice as large didn't require twice the classical computation. It required squaring or exponentiating the previous requirement, depending on the specific problem structure. The The search problems that pervaded computer science shared this exponential character. Finding a specific item in an unsorted database of n entries required examining an average of n divided by 2 entries classically. Finding an item in a database of 1,000,000 entries took 1,000 times longer than finding one in a database of 1,000 entries. The relationship was linear, but for truly large searches, even linear scaling became prohibitive. Searching for patterns in datasets containing billions or trillions of entries consumed time measured in years. Graph problems, where you needed to find paths through networks of connected nodes, exhibited similar scaling challenges. Finding the shortest route through a small network was manageable. Scaling to realistic networks with millions of nodes and billions of connections pushed classical algorithms to their limits. Problems like optimal network routing, supply chain optimization, and scheduling involved graphs too large to search exhaustively, forcing reliance on heuristics that found acceptable solutions without guarantees of optimality. Machine learning systems, training on massive datasets, faced computational walls as the complexity of models grew. Adding more parameters to a neural network, increasing its capacity to learn subtle patterns, multiplied the computation required for training. The largest models pushed the boundaries of what clusters of thousands of processors could accomplish in reasonable time. The appetite for more sophisticated models, capable of learning more nuanced relationships, exceeded the ability to train them. Climate modeling needed to simulate atmospheric, oceanic, and terrestrial systems at resolutions fine enough to capture relevant phenomena while spanning timescales from hours to decades. The computational demands were staggering, requiring the fastest available supercomputers running for weeks to produce single long-term forecasts. Higher resolution, better accuracy, longer prediction horizons, all remain tantalizingly out of reach, limited not by understanding, but by available computation. Financial modeling confronted similar challenges when attempting to price complex derivatives, assess portfolio risk across correlated assets, or simulate market behavior under various scenarios. The models required Monte Carlo simulations running thousands or millions of possible futures, each one computationally expensive. The ensemble needed for statistical confidence exceeding practical computation budgets. Traders made decisions based on approximate models because precise models couldn't run fast enough to be useful. The protein folding problem exemplified the challenge at its most stark. Proteins folded into three-dimensional shapes determined by quantum mechanical interactions between their constituent atoms. Predicting the final folded structure from the amino acid sequence required simulating these interactions, tracking how the protein explored possible configurations, settling into its lowest energy state. The number of possible configurations exceeded comprehension, making exhaustive simulation impossible. Biological proteins folded in milliseconds. Simulating that folding could take years. All these problems shared a frustrating characteristic. You could see what solving them would enable, could articulate why the solutions mattered, could sometimes verify a proposed solution quickly, even though finding it was hard. The gap between knowing a problem was important and being able to solve it created tension. Resources were being allocated to computation that everyone understood was fundamentally inadequate, pursuing incremental improvements when what was needed was a qualitative leap. The need wasn't for faster classical computers, but for a different kind of computer entirely, one that could handle superposition and entanglement natively, that scaled differently with problem size, that matched its computational substrate to the quantum nature of the problems most resistant to classical solution. The physics suggested such a device might be possible. Whether it could be built, made reliable, and scaled to useful sizes remained open questions that would require decades of patient work to answer. The theoretical foundations emerged from quantum mechanics itself, from the strange mathematics that described particles existing in multiple states simultaneously until observed. A classical bit held either 0 or 1, a definite value at any given moment. A quantum bit, a qubit, could exist in a superposition of both states, a linear combination weighted by complex probability amplitudes. This wasn't uncertainty about which state it occupied, but a genuine simultaneous occupation of both, collapsing to a definite value only when measured. The mathematics of superposition allowed a single qubit to represent both 0 and 1 at once. 2 qubits could represent all 4 possible combinations of 2 bits simultaneously. 3 qubits represented 8 states. The pattern continued exponentially. N qubits could represent 2 to the power of n states in superposition. This exponential scaling mirrored the exponential difficulty of the problems quantum computers might address, suggesting a fundamental alignment between the computational substrate and the problem structure. Entanglement provided another resource unavailable to classical systems. 2 entangled qubits exhibited correlations that couldn't be explained by any local hidden variables, measurements on one instantly affecting the state of the other, regardless of separation. This wasn't communication faster than light, but rather a deeper connection, the entangled pair forming a single quantum system that couldn't be described by treating each qubit independently. Operations on entangled qubits could create interference patterns impossible with classical bits. The theoretical models for quantum computation specified how these quantum resources could be harnessed. A quantum algorithm would prepare qubits in an initial state, apply a sequence of quantum gates that manipulated superpositions and created entanglement, allow the quantum state to evolve in ways that amplified the amplitude of the desired answer while suppressing wrong answers, then measure the final state to read out the result. The measurement collapsed the superposition, yielding a classical answer drawn from the quantum probability distribution. The gates themselves were fundamentally different from classical logic gates. A classical AND gate took 2 input bits and produced 1 output bit, destroying information irreversibly. Quantum gates had to be reversible, preserving information to maintain quantum coherence. They operated by rotating quantum states in abstract vector spaces, changing the amplitudes of different basis states without collapsing the superposition. The mathematics involved unitary matrices, ensuring that probabilities remain normalized, that the quantum state evolved in physically valid ways. Certain quantum gates operated on single qubits, rotating their state around various axes in the abstract space where superpositions lived. Others operated on pairs of qubits, creating entanglement or conditional operations where one qubit state determined how operations affected another qubit. These gates could be combined into circuits, sequences of operations that processed quantum information, the output of one gate feeding into the input of the next, building up complex transformations of the quantum state. The theoretical power came from exploiting quantum parallelism. Operations applied to superpositions affected all the states in the superposition simultaneously. A function evaluated on a superposition of all possible inputs produced a superposition of all corresponding outputs in a single operation. This wasn't true parallelism in the classical sense. You couldn't simply read out all the answers because measurement would collapse the superposition to a single result. But clever algorithms could arrange interference such that wrong answers cancelled out, while the correct answer's amplitude grew large enough to be measured reliably. The first theoretical algorithms demonstrated concrete advantages over classical approaches for specific problems. The database search algorithm showed how quantum computers could search unsorted databases quadratically faster than classical computers, examining roughly the square root of n entries to find an item in a database of size n. This wasn't exponential speedup, but the improvement was significant for large searches, and the algorithm was elegant, using amplitude amplification to boost the probability of measuring the correct answer. The factoring algorithm provided a more dramatic example, showing that quantum computers could factor large numbers exponentially faster than the best-known classical algorithms. The approach was indirect, reducing factoring to finding the period of a mathematical function, then using quantum Fourier transforms to extract that period efficiently. The algorithm was complex, requiring careful preparation, controlled operations, and measurement in a transformed basis. But the theoretical speedup was undeniable and had immediate implications for cryptographic security. These early algorithms proved that quantum computation wasn't just theoretically different from classical computation, but could solve certain problems faster, sometimes dramatically faster. The challenge shifted from whether quantum computers could offer advantages to whether they could be built, whether the theoretical models could be realized in physical systems that maintained quantum coherence long enough to perform useful computation. The search for physical systems that could serve as qubits required meeting exacting requirements. The system needed discrete quantum states that could be distinguished and manipulated individually. These states had to remain coherent, maintaining their quantum superposition and entanglement long enough to perform many operations. The system needed to be controllable, allowing precise application of quantum gates. and it needed to be measurable, allowing the final quantum state to be read out as classical information. Atoms offered natural candidates, with electrons occupying discrete energy levels. Two levels could represent 0 and 1, excited and ground states distinguishable by their energy. Lasers could manipulate these states, driving transitions between levels with precisely timed pulses. Magnetic fields could shift energy levels, tuning the qubit frequency. The challenge was isolating atoms sufficiently from their environment to maintain coherence while still being able to control and measure them. Ion traps confined charged atoms using electromagnetic fields, holding them in ultra-high vacuum where environmental interactions were minimal. The ions could be laser-cooled to near motionless, their quantum states protected from thermal noise. Multiple ions could be trapped in a line, their collective vibration modes providing a bus for creating entanglement between distant qubits. The control was exquisite: individual addressing of specific ions, precise timing of laser pulses, careful calibration of field strengths. Neutral atoms could be trapped using optical dipole forces. Lasers creating potential wells that confined atoms without requiring them to be charged. Arrays of these traps could be created using holographic techniques, positioning atoms in programmable geometries. The atoms could be made to interact through carefully tuned excitation to highly excited Rydberg states, where the electron orbited far from the nucleus and the atom became enormous by atomic standards, allowing interactions between neighboring atoms. Photons, particles of light, provided another qubit candidate. The polarization of a photon could encode quantum information, horizontal and vertical polarization representing 0 and 1, arbitrary superpositions accessible through waveplates. Entangled photon pairs could be created through nonlinear optical processes, their polarizations correlated in ways that violated classical expectations. Photons had the advantage of traveling at light speed and interacting weakly with their environment, maintaining coherence easily, but the disadvantage of being difficult to store or hold stationary. Superconducting circuits offered a solid-state approach, using the quantum properties of electrical oscillations in circuits cooled to temperatures approaching absolute zero. At these extreme cold temperatures, certain materials exhibited superconductivity, allowing current to flow without resistance, electrical behavior becoming quantum mechanical in nature. Circuits could be designed where the quantum state was the direction of current flow, or the number of magnetic flux quanta threading a superconducting loop, or the charge state of a capacitor island. These superconducting qubits were macroscopic quantum objects, circuits visible to the naked eye, behaving quantum mechanically because they were cold enough and isolated enough that thermal fluctuations couldn't destroy quantum coherence. They could be fabricated using semiconductor manufacturing techniques, patterns of superconducting metal and insulators deposited on silicon wafers. This offered a path to scaling, creating many qubits on a single chip. though each chip would require elaborate cooling and control infrastructure. Spin systems provided yet another option, using the magnetic moment of electrons or nuclei as the quantum degree of freedom. An electron's spin could point up or down along a magnetic field axis, the superposition of these states representing the qubit. Nuclear spins in molecules offered exceptional coherence times. The nuclear magnetic moment shielded from environmental noise by the surrounding electron cloud. The challenge was controlling individual nuclear spins precisely, distinguishing them from their many neighbors in a solid or liquid sample. Each physical implementation offered different trade-offs. Atomic systems provided excellent coherence, but were difficult to scale to many qubits. Superconducting circuits could be scaled more readily, but required millikelvin temperatures and suffered shorter coherence times. Photonic approaches enabled fast gates and easy routing, but struggled with qubit storage and 2-qubit interactions. The diversity of approaches reflected the fundamental difficulty. No system naturally satisfied all requirements simultaneously. The theoretical framework for quantum error correction offered hope that imperfect physical qubits could be combined to create more reliable logical qubits. By encoding one logical qubit across multiple physical qubits and performing syndrome measurements to detect errors without collapsing the quantum state, it was theoretically possible to suppress errors exponentially with the number of physical qubits used. This required that error rates stay below certain thresholds and that errors were sufficiently uncorrelated, but it provided a path forward even if individual qubits remained imperfect. The early conceptual work established both the promise and the challenge. Quantum computers could theoretically solve certain problems much faster than classical computers. Multiple physical systems could serve as qubits, each with advantages and disadvantages. Error correction could potentially overcome the fragility of quantum states. What remained was the engineering, building systems that actually worked, that could be controlled with sufficient precision, that could scale to numbers of qubits large enough to outperform classical computers on problems anyone cared about. The gap between theoretical possibility and working hardware spanned decades of patient development, each small advance building on previous work, each incremental improvement enabling the next. The earliest experimental demonstrations focused on showing that quantum gates could be performed at all, that superposition could be created and maintained, that measurement could extract information from quantum states. These were proof of concept experiments, working with 1 or 2 qubits, demonstrating basic operations rather than useful computation. The control systems required for manipulating quantum states demanded precision beyond what existed in standard laboratory equipment. Laser frequencies needed stabilization to parts per billion, locked to atomic transitions or optical cavities to eliminate drift. Microwave sources driving superconducting qubits required phase coherence over timescales far exceeding commercial signal generator specifications. Magnetic field stability demanded shielding from the Earth's field, from nearby electrical currents, from elevators moving in adjacent buildings. The environmental isolation necessary to maintain quantum coherence shaped every aspect of the experimental apparatus. Temperature control became critical as implementations pushed toward lower energies to minimize thermal excitation. Dilution refrigerators cooled superconducting circuits to millikelvins, a few thousandths of a degree above absolute zero, requiring stages of progressively colder shields, each one removing heat from the stage below. The cooling process was slow, taking hours or days to reach base temperature, and the cold stages had limited cooling power, forcing careful attention to heat loads from wiring, bringing control signals in and measurement signals out. The wiring itself presented engineering challenges unique to quantum systems. Hundreds or thousands of control lines needed to penetrate from room temperature to millikelvin stages, each line potentially conducting heat that would warm the quantum processor. Attenuators and filters along the signal path reduce thermal noise reaching the qubits while maintaining adequate signal strength for control. The routing resembled plumbing more than electronics. Careful attention paid to thermal anchoring at each temperature stage, to avoiding ground loops, to minimizing crosstalk between adjacent lines. Measurement systems needed to detect tiny signals without adding excess noise that would degrade qubit states. Superconducting amplifiers operated near the quantum limit, adding the minimum noise allowed by quantum mechanics. But even this noise accumulated when cascaded through multiple amplification stages. The readout typically converted quantum information to a microwave signal that could be amplified, filtered, and digitized, the entire chain requiring calibration and optimization to maximize the signal-to-noise ratio while minimizing the measurement's back action on the qubit. Calibration procedures consumed significant time, each qubit needing individual characterization before useful operations could begin. The resonance frequencies of qubits varied slightly due to manufacturing tolerances, requiring measurement and adjustment of control parameters. The pulse shapes that implemented quantum gates needed optimization, balancing speed against fidelity, accounting for the qubit's anharmonicity, and coupling to its environment. Crosstalk between qubits required mapping and compensation, ensuring that operations on one qubit didn't inadvertently affect its neighbors. The coherence times, measuring how long quantum information survived before decaying, improved gradually through incremental refinements in materials and fabrication. Early superconducting qubits maintained coherence for nanoseconds, barely enough to perform a single gate operation. Understanding and eliminating loss mechanisms pushed coherence into microseconds, then tens of microseconds. Each order of magnitude improvement required identifying and addressing new limiting factors: surface defects, impurities in materials, coupling to two-level systems in dielectrics, residual magnetic flux, photon shot noise in the control lines. The fabrication processes borrowed from semiconductor manufacturing, but required adaptation for quantum applications. surface preparation became critical, with atomic scale contamination affecting qubit performance. Deposition of superconducting films required controlling thickness to nanometer precision, maintaining stoichiometry, minimizing defects. The substrates themselves mattered, with different crystal orientations and surface treatments producing measurably different qubit properties. The processing happened in specialized facilities where cleanliness standards exceeded even semiconductor fabs, particle counts measured at the molecular level. Testing individual qubits required equipment that could operate at cryogenic temperatures while providing the full suite of control and measurement capabilities. The test setups resembled miniature versions of full quantum computers, with similar wiring complexity and calibration requirements. Characterization protocols measured qubit frequency, coherence times, gate fidelities, readout performance, susceptibility to various noise sources. The data guided iterations on design and fabrication, closing the loop between measurement and improvement. Scaling from single qubits to multi-qubit systems introduced new challenges. Qubits needed to couple to each other strongly enough for fast 2-qubit gates, but weakly enough to remain individually addressable. The coupling could be direct, through physical proximity and shared electromagnetic fields, or mediated through resonators that connected distant qubits. Each approach had trade-offs in gate speed, crosstalk, connectivity, and susceptibility to fabrication variations. The classical control electronics supporting quantum processors grew in complexity as qubit counts increased. Each qubit required multiple control channels, typically separate lines for driving transitions and readout. The digital to analog converters generating control pulses needed high sampling rates and many bits of amplitude resolution to create arbitrary waveforms. Field programmable gate arrays orchestrated the timing, synchronizing operations across many qubits, implementing feedback loops where measurement results determine subsequent control pulses. The software layers mediating between high-level quantum algorithms and low-level hardware operations grew increasingly sophisticated as the systems became more capable. Compiler toolchains translated abstract circuit descriptions into specific sequences of pulses optimized for the target hardware. These compilers had to map logical qubits to physical qubits, route operations through available connectivity, decompose multi-qubit gates into sequences of native gates the hardware could execute, schedule operations to minimize idle time while respecting hardware constraints. Pulse-level control opened opportunities for optimization unavailable at the gate level. Rather than treating gates as abstract operations, pulses could be shaped to implement gates more efficiently, suppressing unwanted transitions, compensating for crosstalk, implementing composite sequences that corrected certain errors. The optimal pulses depended on detailed models of the qubit Hamiltonian, on measured parameters from calibration, on numerical optimization that explored the space of possible pulse shapes, searching for improved fidelity. The middleware managing quantum experiments handled resource allocation across multiple users, queued jobs waiting for hardware access, prioritized workloads by various criteria. It integrated with classical computing infrastructure, allowing hybrid algorithms that alternated between quantum and classical processing, optimized parameters classically based on quantum measurements, iterated until convergence criteria were met. The system tracked qubit performance over time, automatically recalibrating when metrics degraded beyond acceptable thresholds. Error mitigation techniques attempted to reduce the impact of noise on computation results without the overhead of full error correction. These classical post-processing methods used measurements from multiple circuit runs to estimate and subtract the effect of certain error processes. Other approaches inserted randomized operations that converted coherent errors into incoherent noise, which was easier to characterize and compensate. The methods provided useful improvements for near-term systems not yet capable of implementing error correction. Benchmarking protocols assessed quantum processor performance across various metrics. Randomized benchmarking measured average gate fidelities by applying random sequences of gates that should return the qubit to its initial state, measuring how often this actually occurred. Cross-entropy benchmarking sampled from quantum circuits expected to produce hard-to-predict output distributions, verifying that the quantum processor produced the predicted statistics better than classical simulation could explain. Quantum volume attempted to capture overall system capability in a single metric accounting for qubit number, connectivity, and gate fidelity. The development of quantum programming languages and frameworks lowered barriers to using quantum processors. High-level abstractions allowed expressing quantum algorithms without worrying about hardware details. Libraries provided implementations of common routines, quantum Fourier transforms, amplitude amplification, variational ansatzer. Simulators allowed testing on classical hardware before running on actual quantum processors, debugging circuits, validating results against known cases where classical simulation remained feasible. The user communities that formed around available quantum systems drove usage patterns and identified needs. Researchers explored quantum chemistry applications, simulating molecular energies and reaction dynamics. Machine learning practitioners experimented with quantum kernels and variational classifiers. Optimization specialists investigated quantum approaches to combinatorial problems. Cryptographers studied both quantum attacks on classical encryption and quantum secure alternatives. Each domain developed its own methodologies, best practices, benchmark problems. Collaboration tools enabled distributed teams to work with quantum hardware, sharing access to expensive resources, publishing circuit designs and results, comparing implementations across different hardware platforms. Cloud access to quantum processors democratized experimentation, allowing researchers without dedicated quantum labs to run experiments, students to learn through hands-on experience, developers to prototype applications. The remote access introduced its own challenges: queuing delays, limited real-time interaction, difficulty debugging when the hardware was physically distant and inaccessible. Educational initiatives trained the growing workforce needed to develop quantum technologies. University courses covered quantum mechanics, quantum information theory, error correction codes, algorithm design. Laboratory courses provided hands-on experience with quantum hardware, often accessed remotely. Industry training programs focused on practical skills, calibrating qubits, characterizing noise, optimizing circuits for specific hardware. The field drew from diverse backgrounds: physicists, electrical engineers, computer scientists, mathematicians, each bringing relevant expertise to different aspects of the challenge. The standards efforts attempted to establish common frameworks as the field matured. Benchmark suites for comparing different quantum processors, file formats for describing quantum circuits, calibration protocols for reporting qubit performance. These standards facilitated comparison across systems, enabled portability of software, established common vocabulary for discussing performance. The standards had to balance specificity needed for meaningful comparison against flexibility to accommodate diverse approaches and rapid technological evolution. The accumulation of knowledge, tools, techniques, and infrastructure transformed quantum computing from isolated experiments to an emerging technology ecosystem. The pieces were assembling: hardware platforms demonstrating improved performance, control systems enabling precise manipulation, software stacks abstracting hardware complexity, user communities driving applications. What remained was scaling to larger systems, improving reliability, demonstrating advantages over classical computation on problems of practical interest. The physical construction of quantum processors required environments that isolated delicate quantum states from the chaos of the thermal world. The refrigeration systems that achieved near absolute zero temperatures operated through stages of progressively sophisticated cooling mechanisms. Liquid nitrogen provided the first stage, cooling to 77 Kelvin, a temperature where many materials became brittle and electrical properties shifted dramatically. This stage intercepted the bulk of heat radiation from room temperature, preventing it from reaching colder stages below. Below the nitrogen stage, pulse tube coolers used compressed helium gas expanding through carefully designed valves to extract heat mechanically. These closed-cycle systems required no consumable cryogens, running continuously for months or years, but they introduced vibrations from the compressor and cold head motion. Isolation mounts attempted to decouple the mechanical vibrations from the quantum processor using springs, dampers, and mass to attenuate oscillations that could couple energy into the qubits and degrade coherence. The final cooling to millikelvin temperatures exploited the quantum properties of helium-3 and helium-4 isotopes mixing at low temperatures. In a dilution refrigerator, helium-3 dissolved into helium-4 in one chamber and was pumped out in another. The enthalpy change of mixing extracting heat from the coldest stage. The process was continuous once started, circulating helium through heat exchangers, progressively cooling the incoming flow, maintaining the mixing chamber at temperatures measured in thousandths of a degree above absolute zero. The packaging of the quantum processor itself balanced accessibility for wiring against isolation from environmental noise. Superconducting chips mounted in metal housings that provided electromagnetic shielding. The cases carefully designed to avoid creating resonances at frequencies where qubits operated. Wire bonds connected chip pads to package pins. These tiny gold or aluminum wires carrying signals between the fragile chip surface and more robust connectors. The bonds had to be mechanically stable through thermal cycling, maintaining electrical contact as materials contracted and expanded with temperature changes. The microwave control signals reached qubits through coaxial cables, layers of conductor and dielectric maintaining controlled impedance from room temperature to millikelvin stages. At each temperature stage, attenuators dissipated signal power, adding loss intentionally to reduce thermal noise propagating down the lines. The attenuation values were carefully chosen to balance reduced noise against maintaining sufficient signal amplitude for control. Too much attenuation required higher room temperature power, increasing heat load on intermediate stages. Too little allowed excess noise to reach the qubits. Filters blocked frequencies outside the narrow bands needed for qubit control, preventing unwanted signals from coupling into the quantum system. The filters used various technologies: lumped element circuits at higher temperatures, distributed transmission line structures at intermediate stages, specialized superconducting filters at the coldest stages where they could achieve extremely sharp cutoffs. Each filter added insertion loss at the desired frequencies, another factor in the power budget. But the protection from out-of-band noise justified the cost. The amplification chain for qubit readout started at the coldest accessible stage with quantum-limited amplifiers. These devices operated near the fundamental limit imposed by the uncertainty principle, adding minimal noise to the signal being amplified. The amplifiers were themselves sensitive devices, requiring careful biasing, protection from overload, thermal anchoring to maintain operating temperature. Their gain allowed the tiny microwave signals carrying qubit information to be boosted above the noise floor of room temperature electronics. Higher temperature amplification stages provided additional gain, each one operating at progressively higher temperatures where noise performance mattered less because the signal had already been amplified above room temperature noise levels. The cascade typically included a low noise amplifier still at cryogenic temperatures, but above millikelvins. Then room temperature amplifiers, providing the final gain needed for digitization. Isolators between stages prevented reflections from propagating backward, protecting sensitive amplifiers from damage and reducing standing waves that could affect measurement fidelity. The digitization of qubit signals happened at room temperature using high-speed analog to digital converters. These converters sampled the amplified microwave signals at rates exceeding 1 billion samples per second, capturing the time evolution of the qubit state during measurement. The digital samples fed into processing pipelines that down-converted to baseband, filtered, and integrated over the measurement window, to extract the final readout value. Field programmable gate arrays perform these operations in real time, producing binary measurement results within microseconds. The mechanical stability of the entire apparatus mattered at surprising scales. Vibrations at kilohertz frequencies could modulate cavity resonances or qubit frequencies through physical motion of components. Acoustic noise in the lab, coupled through mounting structures into the cryogenic system. Even the building's motion from wind loading or nearby traffic created measurable effects on qubit coherence in some systems. Isolation required massive support structures, sometimes floating on air springs, acoustic enclosures around the refrigerator, careful routing of plumbing and electrical connections to minimize mechanical coupling. The magnetic shielding necessary to protect qubits from environmental fields used multiple layers of high permeability metal, each layer attenuating external magnetic fields by factors of 10 to hundreds. The shields formed nested cylinders around the quantum processor, with careful attention to joints and penetrations where fields could leak through. Active compensation coils generated fields to null residual components that penetrated the passive shielding, maintaining field stability measured in nanotesla as external conditions changed. The cleanroom environments where quantum processors were fabricated enforced discipline, unlike anything in typical manufacturing. Air entered through ceiling-mounted HEPA filters in laminar flow, descending at controlled velocity, exiting through perforated floor panels. The air changed completely every few minutes, each cubic meter passing through filters that removed particles down to submicron sizes. Workers wore full cleanroom suits, bunny suits covering every hair, every exposed skin surface, preventing human contamination from reaching the pristine silicon wafers. The photolithography tools that patterned quantum circuits operated with nanometer precision, aligning multiple layers with registration tolerances tighter than the wavelength of visible light. The alignment procedure used infrared illumination to see through the silicon substrate, locating alignment marks from previous layers, compensating for wafer distortion from thermal processing. The exposure happened under deep, ultraviolet light. The pattern transferred from a photomask to light-sensitive resist coating the wafer surface. Development of the exposed resist revealed the pattern, selective removal creating openings where the substrate would be etched or material deposited. The development chemistry had to be fresh, the temperature controlled, the timing precise. Overdevelopment eroded pattern fidelity. Underdevelopment left residues that would interfere with subsequent processing. The developed wafers were inspected optically before proceeding, defects catalogued, patterns measured to verify they matched design intent. The etching processes that removed unwanted material operated through chemical or physical mechanisms. Wet etches used liquid acids or bases that reacted with specific materials, dissolving them at controlled rates. Dry etches use plasma, ionized gases that combine chemical reaction with physical bombardment. achieving anisotropic profiles where vertical sidewalls were maintained. The etch depth required precise timing, measuring removal rate on test wafers, adjusting process parameters to hit target dimensions within nanometers. Metal deposition built up the superconducting circuits that would form qubits and resonators. Physical vapor deposition techniques, sputtering or evaporation, transferred metal from a source to the wafer surface atom by atom. The deposition rate, substrate temperature, and chamber pressure all affected the resulting film's properties. Superconducting quality depended on crystal structure, grain boundaries, surface roughness, all influenced by deposition conditions. Post-deposition annealing sometimes improved properties, allowing atoms to rearrange into more ordered configurations. The Josephson junctions that provided nonlinearity essential for quantum computation required specialized fabrication. Two superconducting electrodes were separated by a thin insulating barrier, typically aluminum oxide, just a few nanometers thick. Electrons could tunnel quantum mechanically through this barrier, the tunneling resistance and junction capacitance determining the junction's electrical properties. The oxidation step that created the barrier was critical. Too thin, and the junction would be too conducting; too thick, and it would be too insulating. The oxidation happened in controlled environments, pure oxygen at specific pressures for calibrated times. The junction fabrication often used shadow evaporation, tilting the substrate during metal deposition to create overlapping electrodes separated by the oxide barrier. The technique required careful control of evaporation angles, substrate rotation, and etch depth in the resist that defined the junction pattern. The two metal layers had to make contact elsewhere on the chip for wiring, requiring additional patterning steps, multiple depositions, selective etching to create the complete circuit. The resist removal after patterning had to be thorough, stripping organic material without damaging the underlying structures. Plasma ashing oxidized the resist, breaking long polymer chains into volatile fragments that could be pumped away. Solvent rinses removed ash residues and any remaining contamination. The cleaned wafers were inspected again, optical and electron microscopy, verifying that patterns matched specifications, that junctions appeared uniform, that no obvious defects would compromise device performance. Dicing separated individual chips from the processed wafer, diamond saws cutting through the silicon along scribe lines between devices. The saw parameters, blade speed, feed rate, cutting depth, were optimized to minimize chipping and mechanical stress while achieving clean separation. The singulated chips were cleaned again to remove debris from sawing, then sorted according to which would proceed to packaging and which would be saved for later use or analysis. The assembly of chips into packages required precision placement and delicate handling. Chips were picked from carrier wafers using vacuum tools, positioned in package cavities, bonded to the package floor using adhesives or eutectic bonding that created electrical and thermal contact. The bond needed sufficient strength to survive thermal cycling and mechanical stress, while maintaining low thermal resistance to conduct heat away from the chip during operation. Wire bonding connected chip pads to package leads using gold or aluminum wire, 25 to 50 microns in diameter. The bonding tool applied pressure and ultrasonic energy, creating a metallurgical bond between the wire and the pad without melting either material. Each bond had to be individually formed, the tool positioning over the bond site, descending to make contact, forming the bond, then lifting and moving to the next location. Hundreds of bonds might be required for a single chip, each one a potential failure point, requiring careful inspection. The final package sealing protected the chip from moisture and contamination during storage and operation. Metal lids were welded or brazed in controlled atmospheres, sometimes backfilling with inert gas to prevent oxidation during subsequent thermal cycling. The sealed packages underwent leak testing, helium introduced at pressure, then detected with mass spectrometers sensitive to minute leak rates. Packages that failed leak testing were rejected, the chips potentially salvageable by removing them and attempting repackaging. The diversity of quantum computing approaches created challenges for establishing common frameworks. Each physical implementation, superconducting circuits, trapped ions, neutral atoms, photonic systems, operated according to different principles, required different control methods, exhibited different noise characteristics. Yet the need for standardization grew as the field matured, as more groups built systems, as users wanted to write programs that could run across different hardware platforms without complete re-implementation. The quantum circuit model provided the most universal abstraction, a language for describing quantum algorithms independent of physical implementation. Circuits consisted of qubits initialized to standard states, sequences of quantum gates applied to those qubits, and measurements that extracted classical information from the final quantum state. This model worked across platforms because it captured the essential structure of quantum computation without committing to specific gate implementations or physical qubit types. The gate sets that different systems could implement natively varied considerably. Superconducting systems typically offered arbitrary single qubit rotations and a 2-qubit entangling gate, often a controlled phase or cross-resonance interaction. Ion trap systems provided similar single qubit control through laser pulses, but used phonon-mediated interactions for 2-qubit gates. Neutral atom systems could implement gates through Rydberg interactions between atoms. Photonic systems relied on beam splitters and phase shifts for single qubit operations, with 2-qubit gates requiring photon detection and feed forward. The compilation problem translated circuits written in a universal gate set into the native operations of specific hardware. This required decomposing arbitrary gates into sequences of available gates, routing logical operations through the physical connectivity constraints of the hardware, optimizing for total circuit depth or gate count. The compilation strategies differed between platforms, reflecting their different strengths. Ion systems with all-to-all connectivity could implement any 2-qubit gate directly, while superconducting systems with limited connectivity needed to route through chains of swap operations. The measurement standard specified how quantum states were read out and how results were reported. Most systems performed measurements in the computational basis, projecting qubits onto definite 0 or 1 states, but the assignment of which physical state corresponded to which logical value could be arbitrary and platform-dependent. Calibration procedures determined the threshold for discriminating measurement outcomes, optimizing readout fidelity, characterizing readout errors, including false positive and false negative rates. The error models that describe noise processes differed between implementations, but needed common frameworks for comparison. Depolarizing noise treated all Pauli errors as equally likely. Amplitude damping modeled energy relaxation to the ground state. Dephasing captured pure information loss without energy exchange. Measurement errors included both readout mistakes and back action on unmeasured qubits. Each platform exhibited its characteristic error signatures, but expressing them in standard models allowed meaningful performance comparisons. The benchmarking protocols that assessed quantum processor performance became standardized across the field. Single qubit and 2-qubit randomized benchmarking measured average gate fidelities using sequences of random gates. Gate-set tomography reconstructed complete descriptions of gate operations and errors. Process tomography characterized how quantum channels transformed input states to output states. These protocols produced metrics that could be compared across platforms despite differences in underlying physics. The programming languages developed to express quantum algorithms converged on common syntax and semantics. Circuit descriptions specified qubit registers, gate operations, classical registers for measurement results, and control flow including conditional operations. Higher-level abstractions allowed expressing algorithms without gate-level detail, compilers translating to circuits automatically. The languages supported both low-level pulse control for optimization and high-level algorithm description for portability. The simulation tools that allowed testing quantum circuits classically adopted standard interfaces. Simulators could exactly reproduce quantum dynamics for small numbers of qubits, providing ground truth for validation. Approximate simulators traded accuracy for scale, handling more qubits by using tensor network methods or other techniques that captured important correlations while discarding less relevant information. Noisy simulators modeled realistic error processes, predicting how circuits would perform on actual hardware. The cloud access models that let remote users submit jobs to quantum processors required standard protocols. Jobs were specified as circuits with associated metadata, which qubits to use, how many shots to run, priority level, maximum runtime. Queue management systems handled multiple users, allocated resources fairly, enforced usage quotas. Results were returned with standardization, that included raw measurement counts, calibration data, contemporary with the run, timestamps, and the hardware configuration details. The calibration data that characterized quantum processor state became standardized in format and content. Qubit frequencies, coherence times, gate fidelities, readout errors, crosstalk matrices, all needed to be reported in ways that users and analysis tools could parse consistently. The calibration cadence varied by platform. Some systems required daily recalibration. Others remained stable for weeks. Users needed to know how recent calibration data was to judge result reliability. The error mitigation and correction codes required common implementations to be portable across systems. Repetition codes, surface codes, and other quantum error correction schemes could be expressed abstractly, but needed platform-specific compilation. Error mitigation techniques like zero-noise extrapolation or probabilistic error cancellation could be implemented at the software layer, applying to any underlying hardware, but their effectiveness depended on characterized noise models. The communication protocols between classical control systems and quantum processors needed standardization as architectures grew complex. The timing precision required for quantum operations demanded synchronized clocks across distributed control electronics. Phase coherence between control signals had to be maintained over timescales spanning many operations. Trigger signals coordinating measurement with subsequent operations required picosecond level timing jitter to avoid degrading gate fidelity. The pulse level control specifications defined how quantum gates were implemented at the most fundamental level. Pulses were characterized by amplitude, frequency, phase, and envelope shape as functions of time. The pulse shaping used various techniques: Gaussian envelopes, minimizing spectral leakage, drag corrections, suppressing leakage to non-computational states, composite pulses, correcting systematic errors through carefully designed sequences. Each technique required parameters that needed standard representation for sharing and reproduction. The connectivity graphs that described which qubits could interact directly varied dramatically between architectures. Superconducting systems typically had nearest neighbor connectivity on one- or two-dimensional lattices. Ion trap systems could couple any pair of ions through shared motional modes. Neutral atom systems arranged qubits in reconfigurable geometries, with interaction distance limited by a Rydberg blockade radius. These connectivity constraints fundamentally affected which circuits could be run efficiently, requiring standardized representations for routing and mapping algorithms. The crosstalk characterization quantified unwanted interactions between qubits. Operating on one qubit could shift the frequency of neighbors, introduce phase errors, or cause population transfer. The crosstalk could be coherent, producing systematic unitary errors, or incoherent, adding noise. Characterizing the complete crosstalk matrix required extensive measurements, applying operations to each qubit while monitoring effects on all others. The resulting data informed both circuit compilation and error mitigation strategies. The lifetime and stability specifications indicated how long quantum processors maintained their calibrated performance. Some qubits drifted in frequency over hours due to charge trapping or flux noise. Gate fidelities degraded as the system warmed or as amplifier bias points shifted. Measurement assignments changed as discriminator thresholds drifted. Users needed to know typical stability timescales to design experiments that completed within validity windows of calibration data. The performance metrics reported for quantum processors required context for meaningful interpretation. Qubit coherence times meant little without knowing the gate times, as the relevant figure was how many gates could be performed during coherence. 2-qubit gate fidelity needed to be specified along with gate duration, as slower gates could sometimes achieve higher fidelity. Readout fidelity needed disambiguation between assignment errors in different directions, as false positives and false negatives often differed substantially. The certification procedures that verified quantum processors operated correctly drew from both classical computing and quantum information theory. Classical tests verified that control electronics functioned properly, that signals reached qubits with correct timing and amplitude. Quantum tests verified that gates implemented intended unitary operations, that measurements projected onto correct bases, that noise levels fell within specifications. Certification was ongoing, not one time, as quantum systems required continuous monitoring and periodic recalibration. The interoperability standards allowed different parts of the quantum computing stack to work together. Quantum circuits generated by one compiler could be processed by another optimizer. Calibration data from one characterization tool could inform scheduling decisions in another resource manager. Results from different processors could be combined when distributing computation across multiple systems. This modularity required careful interface definition and data format standardization. The documentation standards specified what information providers needed to supply about their quantum systems. Hardware specifications included qubit modality, coherence times, gate sets, connectivity, error rates. Software interfaces documented available operations, input formats, output structures, rate limits. The documentation needed updating as systems evolved, maintaining accuracy as hardware was upgraded or software capabilities expanded. The versioning schemes tracked changes in both hardware and software components of quantum systems. Hardware versions indicated major architecture revisions, gate set changes, connectivity modifications. Software versions tracked compiler updates, new error mitigation techniques, interface changes. Users needed to specify which versions their code targeted to ensure reproducibility and to understand what features were available. The open source frameworks that implemented quantum algorithms and tools adopted standard software engineering practices. Version control tracked code changes. Testing suites verified correctness across updates. Documentation explained interfaces and usage. License terms clarified permitted uses. The frameworks built communities of contributors, distributed development effort, accelerated progress through collaboration. Standardization made these collaborations possible, allowing work from different groups to integrate cleanly. The educational standards for quantum computing curricula addressed what students should learn at different levels. Introductory courses covered quantum mechanics fundamentals and basic algorithms. Intermediate courses examined error correction, compilation, and characterization techniques. Advanced courses explored research frontiers in fault tolerance, new physical implementations, and application domains. The standardization helped institutions develop programs and helped students understand career paths in the emerging field. The shift from laboratory curiosity to accessible technology happened gradually, marked less by single breakthroughs than by accumulated improvements that crossed invisible thresholds of usefulness. The first quantum processors available through cloud platforms offered handfuls of qubits, their coherence times measured in microseconds, their error rates high enough that most circuits produced noise rather than meaningful results. Yet researchers began probing what could be learned even from these imperfect systems, developing techniques to extract information despite noise, exploring the boundary between quantum and classical computation. The applications that emerged in this early period focused less on outperforming classical computers than on understanding quantum systems themselves. Simulating small molecules to validate quantum chemistry algorithms became standard practice, comparing quantum processor results against exact classical calculations for systems small enough to solve both ways. The comparisons revealed systematic errors, calibration issues, unexpected noise sources. Each discrepancy prompted investigation, improvements to control, refinement of error mitigation techniques. Educational usage flourished as cloud access lowered barriers to hands-on experience with quantum hardware. Students could submit simple circuits, observe measurement statistics, experiment with superposition and entanglement without needing physical access to dilution refrigerators and laser systems. The immediacy of feedback, submitting a circuit and receiving results within minutes or hours, made quantum mechanics tangible in ways that textbook problems never achieved. The pedagogy evolved to incorporate actual quantum hardware into curricula. The artistic community discovered quantum processors as creative tools, using quantum randomness and superposition to generate patterns and sounds. The outputs were genuinely unpredictable. Quantum measurement outcomes determined by probability amplitudes rather than algorithmic pseudo-randomness. Artists incorporated this fundamental uncertainty into generative works, exhibitions that displayed different results from identical quantum circuits, performances where quantum measurements influenced audio or visual elements in real time. Commercial interest grew cautiously, companies exploring whether quantum advantage might emerge for optimization problems relevant to logistics, finance, or resource allocation. The variational algorithms that alternated between quantum and classical processing showed promise, using quantum processors to evaluate objective functions, while classical optimization guided parameter selection. The approach worked even with noisy qubits, as long as the quantum evaluation provided useful gradient information or objective values that classical optimization could exploit. The cybersecurity implications of quantum computing drove defensive preparations despite the technology remaining far from breaking widely used encryption. Organizations began transitioning to quantum-resistant cryptographic algorithms, schemes whose security didn't depend on factoring or discrete logarithms that quantum computers could potentially solve efficiently. The transition was precautionary, acknowledging that data encrypted today might need to remain secure for decades, potentially into an era when quantum attacks became practical. The pharmaceutical industry invested in quantum chemistry applications, hoping to accelerate drug discovery by simulating molecular interactions more accurately. The near-term applications focused on small molecules, where quantum simulation offered marginal accuracy improvements over classical methods. But the experience informed algorithm development for larger systems. Understanding which molecular properties quantum processors could predict reliably, even for toy systems, guided research toward practically relevant calculations. The materials science community explored using quantum computers to discover compounds with desired properties, catalysts, superconductors, battery materials, photovoltaics. The simulations remained limited to simple model systems, but they demonstrated workflows that might scale as quantum hardware improved. The collaboration between domain scientists and quantum computing researchers created feedback loops, application requirements, driving hardware development priorities, hardware capabilities, enabling new classes of simulations. The finance sector investigated quantum approaches to portfolio optimization, risk assessment, and derivative pricing. The problems were naturally suited to quantum algorithms that could explore large solution spaces efficiently, but the required qubit counts and error rates remained beyond current capabilities. The research was preparatory, developing algorithms and building expertise against the possibility that quantum advantage might emerge as hardware scaled. The logistics companies simulated routing and scheduling problems on quantum processors, comparing results against classical heuristics. The quantum approaches rarely outperformed well-tuned classical algorithms on available hardware, but they revealed structural features of the solution spaces, provided novel heuristics that could be implemented classically, suggested hybrid approaches that might offer advantages as quantum processors grew more capable. The machine learning community explored quantum kernels, using quantum feature maps to transform classical data into quantum states. The quantum processor could then evaluate inner products between these quantum states, information that classical systems could use for classification or regression. The advantage, if any, depended on whether the quantum feature space captured relevant structure more efficiently than classical kernel methods. The jury remained out, but the exploration continued. The integration of quantum processors into hybrid computing workflows became standard practice, recognizing that quantum and classical computation complemented rather than competed with each other. The classical systems handled data pre-processing, parameter optimization, result analysis, and storage. The quantum processors executed specific subroutines where quantum superposition and entanglement offered potential advantages. The orchestration between quantum and classical happened through software frameworks that abstracted the heterogeneous hardware. The development tools evolved to hide complexity while preserving access to low-level control when needed. High-level interfaces allowed expressing algorithms in domain-specific terms, molecular Hamiltonians for chemistry, cost functions for optimization, graph structures for combinatorial problems. Middleware translated these into quantum circuits, optimized for specific hardware, compiled to native gate sets. Advanced users could bypass abstractions and work directly with pulses when optimization demanded it. The user experience gradually improved as workflows matured. Initial job submission required formatting circuits in specific syntax, manually specifying every parameter. Later interfaces provided graphical circuit builders, libraries of pre-built components, templates for common algorithms. The learning curve flattened, allowing domain scientists to use quantum processors without becoming quantum computing experts, though understanding the technology's limitations remained essential for interpreting results. The reliability of quantum systems improved through better control electronics, refined fabrication processes, and software compensation for systematic errors. The calibration routines became more comprehensive and faster, characterizing systems in minutes rather than hours, enabling more frequent recalibration to track drift. Automated monitoring detected degradation, triggering recalibration or alerting operators to investigate. The manual tuning that once consumed days of expert effort became largely automated. The error rates declined steadily, coherence times lengthened, gate fidelities improved. Each generation of hardware demonstrated measurable progress, the improvements enabling circuits that were deeper, more complex, more likely to complete successfully. The advance wasn't exponential, but it was persistent, the engineering challenges yielding to sustained effort. Qubits that could perform 10 gates during coherence became qubits that could perform hundreds, then thousands. The scale increased as fabrication yields improved, and packaging could accommodate more qubits. Systems grew from 5 qubits to 50, then toward hundreds. The connectivity improved from nearest neighbor on linear chains to two-dimensional lattices to more flexible topologies. Increased qubit counts didn't automatically confer advantage. Most additional qubits were consumed by error correction overhead, but they expanded the space of problems that could be attempted. The software ecosystem matured around the available hardware. libraries accumulated implementations of useful subroutines. Optimization techniques specific to quantum compilation were discovered and shared. Best practices emerged for error mitigation, for variational algorithm design, for benchmarking results. The collective knowledge of the community grew, encoded in documentation, tutorials, published papers, and informal communication channels. The commercial quantum computing services diversified, offering different hardware types through common interfaces. Users could submit identical circuits to superconducting, ion trap, and neutral atom systems, comparing results across platforms. The competition drove improvements, each platform highlighting its strengths, working to overcome weaknesses. The diversity ensured that multiple approaches continued developing rather than prematurely converging on a single architecture. The hybrid cloud models combined quantum and classical resources seamlessly. Users could request allocations of quantum processor time, classical compute cores, GPUs for parallel processing, high bandwidth connections between components. The scheduling systems optimized resource allocation, minimizing idle time, packing compatible jobs together. The pricing reflected actual resource consumption rather than simple per qubit costs, acknowledging that some circuits required extensive classical pre- and post-processing. The open-source hardware movement began producing designs for quantum control electronics, enabling groups to build their own systems rather than relying entirely on commercial solutions. The designs included field-programmable gate arrays for timing control, digital to analog converters for pulse generation, analog to digital converters for qubit readout. The specifications were detailed enough for reproduction. The documentation included commissioning procedures and calibration protocols. The transition from research prototypes to engineered systems continued, quantum processors becoming more appliance-like, less requiring of constant expert attention. The reliability increased to the point where users could expect their jobs to complete without hardware failures interrupting computation. The predictability improved, calibration data providing accurate forecasts of expected error rates. The accessibility broadened, lowering barriers to entry for new users and new application domains. The silent nature of this transition meant that no single event, the crossing from laboratory equipment to infrastructure, rather, the accumulation of incremental improvements, the gradual expansion of what was routine rather than exceptional, the slow growth of the user community, these collectively represented the shift. Quantum computing remained far from maturity, but it had unmistakably moved from pure research toward early-stage technology. The physical infrastructure supporting quantum computing extended far beyond the quantum processors themselves, encompassing facilities, utilities, and support systems that enabled the delicate quantum operations. The buildings that housed quantum computers required environmental controls, maintaining temperature stability within fractions of a degree, humidity within narrow bands to prevent condensation or static buildup, air cleanliness rivaling semiconductor fabrication facilities. The environmental fluctuations that would go unnoticed in conventional data centers could disrupt quantum coherence or damage sensitive equipment. The power conditioning systems that fed quantum computers filtered incoming electricity to remove voltage spikes, harmonics, and transients that could couple into sensitive electronics. Uninterruptible power supplies bridged momentary outages, preventing disruption during grid fluctuations. Backup generators stood ready for extended outages, ensuring that quantum processors didn't warm to room temperature during power failures, which would require days of cooldown before operations could resume. The electrical infrastructure represented significant capital investment, justified by the value of continuous quantum processor availability. The cooling water systems that removed heat from dilution refrigerator compressors required treatment to prevent biological growth, corrosion, or mineral deposits that would degrade heat transfer efficiency. Closed-loop systems recirculated water through heat exchangers, maintaining flow rates and temperatures within specifications. The water temperature affected compressor efficiency and ultimately the base temperature achievable at the quantum processor. Seasonal variations in ambient temperature required adjustment of cooling water conditions to maintain consistent performance. The compressed gas systems that supplied helium to dilution refrigerators needed purity levels exceeding standard industrial grades. Contamination could poison the helium mixture, degrading cooling power, or introducing impurities that would migrate to cold stages and affect quantum processor performance. Gas recovery systems recaptured helium rather than venting it to atmosphere, both for economic reasons and because helium was a finite resource. The recovery, purification, and recirculation infrastructure represented ongoing operational costs and required regular maintenance. The electromagnetic shielding that protected quantum processors from external fields extended to the room level in some installations. Conductive enclosures formed Faraday cages around sensitive equipment, attenuating radio frequency noise from the environment. The shielding had to be continuous, with special attention to penetrations where cables entered the shielded volume. Even small gaps could compromise shielding effectiveness, allowing external fields to couple to quantum processors despite the elaborate passive shielding around individual systems. The vibration isolation that protected quantum processors from mechanical noise used pneumatic systems, active feedback, or massive passive mounts. The refrigerators sat on platforms decoupled from building structure, isolation stages attenuating vibrations from foot traffic, HVAC systems, or nearby equipment. The effectiveness was verified through accelerometers measuring residual motion at the refrigerator, with requirements often specifying maximum displacement measured in microns or maximum acceleration in milli-Gs. The monitoring infrastructure tracked countless parameters indicating quantum system health and performance. temperature sensors at every stage of refrigerators, pressure gauges on gas lines, flow meters on cooling water, power meters on electrical feeds, all stream data to logging systems. Anomalies triggered alerts, notifying operators of conditions requiring attention. The historical data informed predictive maintenance, identifying degradation trends before failures occurred, scheduling interventions during planned downtime rather than responding to emergencies. The network infrastructure connecting quantum computers to users required high bandwidth and low latency for interactive applications. Fiber optic connections provided gigabit or faster speeds to facilities, ensuring that circuit uploads and result downloads didn't bottleneck on network capacity. The routing used redundant paths, protecting against single-link failures. Quality of service policies prioritized quantum computing traffic during congestion, though the actual data volumes were modest compared to the capacity available. The classical computing infrastructure, collocated with quantum processors, handled pre-processing, post-processing, and hybrid algorithm orchestration. High-performance compute clusters ran classical optimizers, simulated small quantum circuits for validation, analyzed measurement results. The classical resources often exceeded quantum resources in both physical scale and cost, reflecting that quantum advantage applied to specific subroutines rather than entire workflows. The integration required fast interconnects and synchronized scheduling across heterogeneous resources. The software infrastructure managing quantum computing facilities included schedulers allocating processor time, compilers optimizing circuits for hardware, calibration systems maintaining performance, monitoring dashboards displaying system status. These systems had to be robust, handling failures gracefully, maintaining service during software updates, protecting user data and intellectual property. The complexity rivaled that of classical high-performance computing centers, with additional challenges from the specialized nature of quantum hardware. The security infrastructure protecting quantum systems addressed both physical and cyber threats. Physical access controls restricted entry to facilities, logging who accessed areas containing quantum hardware. Surveillance monitored for unauthorized presence or tampering. Cybersecurity protected control systems from network intrusion, encrypted communications between components, authenticated users before granting access. The security had to balance protection against openness, particularly for shared user facilities, where maintaining scientific openness while protecting proprietary work required careful policy design. The logistics of consumables supporting quantum operations involved managing inventories of helium, liquid nitrogen, specialty gases, and cryogenic liquids. The consumption rates varied with system utilization and refrigerator efficiency, requiring forecasting to avoid shortages. Deliveries needed scheduling to ensure supplies arrived before depletion, but not so far in advance that storage capacity was exceeded. Some facilities maintained on-site liquefaction or recovery systems, reducing dependence on external supply chains. The maintenance schedules for quantum systems balanced maximizing uptime against necessary servicing. Some maintenance happened while systems remained cold. Electronics repairs, cable replacements, software updates. Other maintenance required warming systems to room temperature, regenerating molecular sieves in helium lines, replacing vacuum pumps, repairing refrigerator mechanical components. The warm-up and cool-down cycles consumed days, making such maintenance expensive in lost operational time, incentivizing reliability improvements that extended service intervals. The spare parts inventory for quantum systems included components with long lead times, items that couldn't be procured quickly if failures occurred. Custom cryogenic components, specialized amplifiers, unique connectors, all required advanced acquisition and storage against future need. The inventory management balanced cost of holding spare parts against cost of extended downtime, waiting for replacements. Critical components often had redundant backups, allowing immediate swap rather than waiting for repairs. The documentation systems tracking quantum system configuration maintain detailed records of hardware revisions, software versions, calibration parameters, maintenance history. This documentation enabled reproducing results, debugging anomalies, planning upgrades. The records accumulated over years of operation, historical data providing baselines for performance comparisons, revealing long-term trends in component aging or environmental drift. The documentation discipline required enforcing processes that captured changes as they occurred, rather than reconstructing them later. The collaboration tools enabling distributed teams to work with quantum hardware included shared calendars for scheduling access, communication channels for coordinating experiments, repositories for sharing code and data. Remote access to quantum systems needed reliable connections, responsive interfaces, adequate documentation to use systems without local experts available for consultation. The tools had to accommodate diverse skill levels, from expert users optimizing low-level pulses to domain scientists using high-level abstractions. The training programs for quantum system operators developed expertise in maintaining and operating complex infrastructure. The skills required spanned cryogenics, radio frequency engineering, software development, quantum physics, each area deep enough to demand specialists, but integrated enough to require cross-disciplinary understanding. The training combined classroom instruction, hands-on apprenticeship, and ongoing professional development as technology evolved. The workforce requirements grew with the expanding quantum computing industry, creating demand that educational institutions struggled to meet. The standards compliance for quantum facilities addressed building codes, electrical safety, pressure vessel regulations, laser safety, radiation safety, where applicable. Inspections verified compliance. Certifications documented that systems met requirements. The regulatory environment varied by jurisdiction, creating challenges for multinational operations or technology transfer between regions with different standards. Navigating the regulatory landscape required expertise in both quantum technology and applicable regulations. The disaster recovery planning for quantum computing facilities addressed scenarios from minor equipment failures to catastrophic events. Backup systems protected against single points of failure. Geographic distribution provided resilience against regional disasters. Data backups preserved user information and system configuration. Recovery procedures specified steps for restoring operations after interruptions, prioritizing critical systems, testing periodically to verify recoverability. The planning acknowledged that quantum systems represented substantial investments worth protecting through redundancy. The energy efficiency initiatives addressed the significant power consumption of quantum computing infrastructure. Refrigerators consumed kilowatts of electrical power to maintain millikelvin temperatures. Control electronics, classical computers, cooling systems all added to the load. Efficiency improvements in refrigerator design, optimized control, pulse power, heat load reduction through improved wiring, all reduced operational costs and environmental impact. The efficiency metrics balanced power consumption against quantum processor performance, acknowledging that running more qubits or achieving better coherence might justify increased power. The sustainability considerations extended beyond energy to material usage, chemical waste, equipment lifecycle. The helium recovery systems conserved a finite resource. Hazardous materials were handled per regulations, disposed of through certified processes. Equipment reaching end of life was evaluated for refurbishment, repurposing, or recycling, rather than simply discarding. The sustainability practices reflected growing awareness that quantum computing's environmental footprint needed management from the technology's early stages. The economic models for quantum computing infrastructure addressed capital costs, operational expenses, revenue from user fees, or computational services. The costs were substantial: facilities, refrigeration systems, control electronics, staff salaries. Revenue sources included research grants, commercial services, internal organizational value from quantum-enabled capabilities. The economics shaped deployment decisions. Centralized facilities serving many users versus distributed systems serving specific applications, general-purpose processors versus specialized systems optimized for particular problems. The community of practice that developed around quantum computing infrastructure shared knowledge, best practices, lessons learned from failures and successes. Conferences, workshops, and online forums provided venues for exchanging information. Site visits allowed learning from others' implementations. Collaborative projects tackled common challenges too large for individual organizations. The community accelerated progress by sharing rather than duplicating effort, building on collective experience rather than each group solving identical problems independently. The network of quantum computing resources distributed across continents created a global infrastructure that no single institution could replicate alone. Research laboratories, technology companies, government facilities, and academic institutions each contributed unique capabilities, different hardware platforms, specialized expertise. The connections between these nodes allowed sharing of knowledge, collaboration across distances, access to resources that would otherwise remain isolated. The emergence of this network paralleled the early development of classical computing infrastructure, but compressed into a shorter time frame. The data exchanges between quantum computing sites involved more than circuit uploads and measurement results. Calibration procedures developed at one facility informed practices at others. Error mitigation techniques discovered through analysis of one system's noise characteristics transferred to different hardware. Benchmark results allowed comparing performance across platforms, identifying which approaches worked best for specific problem types. The flow of information accelerated progress beyond what isolated development could achieve. The remote access models that enabled distributed research teams to use quantum processors located anywhere required protocols for authentication, resource allocation, and fair usage. Researchers in one time zone could submit jobs that ran during off-peak hours elsewhere, maximizing hardware utilization. The asynchronous nature of most quantum computations allowed batching jobs, running them when resources became available, returning results when ready. The model worked well for research and development, less well for applications requiring interactive response. The standardization of interfaces across different quantum computing platforms enabled portability of software and algorithms. A circuit written for one system could, in principle, run on another, despite different underlying physics. The compilation might be more or less efficient, depending on native gate sets and connectivity, but the logical operation remained consistent. This portability encouraged algorithm development independent of hardware details, allowing researchers to focus on quantum information processing rather than specific implementations. The time zone distribution of quantum computing facilities created natural opportunities for follow-the-sun workflows. Experiments could be designed in one location, submitted to run overnight at a facility in a different time zone, results analyzed the following morning. The global distribution reduced waiting times for access to scarce quantum resources, though the benefit diminished as facilities proliferated and capacity increased. The coordination required careful planning and communication across distributed teams. The collaborative experiments that leveraged multiple quantum computing facilities demonstrated capabilities beyond single systems. Distributed quantum computing, where different parts of a computation ran on separate processors with classical communication between them, showed feasibility despite limitations. The approaches weren't yet efficient enough for practical advantage, but they explored architectural alternatives to monolithic quantum computers, paths that might become relevant as quantum networks developed. The educational outreach that made quantum computing accessible globally relied on remote access to hardware and cloud-based simulation tools. Students in regions without local quantum computing facilities could gain hands-on experience through internet connections. The The democratization of access reduced geographic barriers to entering the field, enabling talent development in diverse locations. The online educational resources, tutorials, and communities supported this distributed learning ecosystem. The economic geography of quantum computing showed concentration in regions with existing strength in advanced technology, deep scientific expertise, and substantial capital for investment. Yet the concentration wasn't absolute, with efforts in many countries to develop indigenous quantum computing capabilities. The geopolitical implications of quantum computing drove national investments, concerns about technological sovereignty, desires to participate in what many viewed as a strategically important technology. The supply chains supporting quantum computing span the globe. Components manufactured in different regions based on specialized capabilities. Dilution refrigerators came from a handful of specialized manufacturers. Superconducting chips were fabricated in facilities with appropriate cleanroom and cryogenic expertise. Control electronics drew on semiconductor industry supply chains. High-quality optical components for photonic quantum systems relied on precision manufacturing capabilities. The distributed production created interdependencies that made quantum computing a fundamentally international endeavor. The intellectual property flows across borders reflected both collaboration and competition. Research publications shared discoveries openly, advancing collective knowledge. Patents protected specific innovations, creating negotiable assets and potential barriers to entry. The balance between openness and protection varied by organization and national context, with academic institutions generally more open, commercial entities more protective, governments somewhere between depending on perceived strategic value. The conferences and workshops that brought together the quantum computing community occurred globally, rotating between continents, attracting participants from worldwide. These gatherings served purposes beyond presentations and proceedings, establishing collaborations, recruiting talent, showcasing capabilities, negotiating partnerships. The face-to-face interactions complemented but didn't replace remote collaboration, providing different communication modes that virtual meetings struggled to replicate. The quantum internet vision imagined networks of quantum computers connected by quantum communication channels, enabling distributed quantum computing and quantum-secured communication. The implementation required quantum repeaters to extend entanglement distribution beyond single-hop distances, quantum memories to store quantum states during routing, and interfaces converting between different physical qubit types. The technical challenges were substantial, the timeline uncertain, but the concept drove research into quantum networking technologies. The entanglement distribution experiments demonstrated quantum correlations shared between distant locations, photons, or atoms entangled and separated by kilometers or hundreds of kilometers. The experiments used fiber optic cables, free space optical links, even satellite-based connections to maintain entanglement across growing distances. The loss in optical channels limited range. The decoherence from environmental noise degraded fidelity, but the experiments proved feasibility and identified engineering challenges requiring solution. The quantum key distribution systems deployed for secure communication represented the most mature quantum networking technology. The systems used quantum states of photons to establish encryption keys between parties, the security guaranteed by quantum mechanics rather than computational difficulty. Eavesdropping attempts necessarily disturb the quantum states, revealing the presence of interception. Commercial systems operated over metropolitan distances, securing financial transactions, government communications, critical infrastructure data. The classical communication infrastructure that supported quantum networking carried auxiliary information needed to extract useful results from quantum channels. The entanglement distribution required classical communication to compare measurement outcomes and verify correlations. The quantum key distribution needed authenticated classical channels to prevent man-in-the-middle attacks. The quantum teleportation protocols required classical bits to accompany quantum transmission. The quantum and classical channels were complementary, neither sufficient alone. The synchronization requirements for quantum networks demanded precision timing across distributed nodes. Entanglement distribution needed coordinated measurements. Quantum gates needed synchronized control pulses. Photon detection required precise timing discrimination. The clock distribution used GPS references, fiber-based frequency transfer, or other methods to maintain synchronization, measured in picoseconds or better. Even small timing errors could degrade performance or introduce errors in quantum protocols. The switching and routing challenges in quantum networks differed fundamentally from classical networks. Quantum states couldn't be copied, preventing standard error correction through redundant transmission. Quantum information couldn't be amplified the way classical signals were, limiting transmission distance. The routing decisions had to preserve quantum coherence, minimize operations that degraded state fidelity. The network architecture required rethinking based on quantum information's unique properties. The modality conversions between different quantum systems enabled hybrid networks combining strengths of different technologies. Microwave photons from superconducting qubits could be converted to optical photons for long-distance transmission through fiber. Atomic qubits could interface with photonic channels through carefully tuned lasers. These conversions were inefficient and challenging, but they allowed heterogeneous networks where different qubit types handled the tasks they performed best. The error rates in quantum communication channels required mitigation and correction strategies. The photon loss, the phase noise, the detected dark counts all introduced errors that accumulated with transmission distance or network hops. Quantum error correction codes could protect against some errors, but required overhead in qubits and operations. Distillation protocols could improve entanglement quality at the cost of success probability. The trade-offs between rate, fidelity, and distance shaped network design choices. The applications envisioned for quantum networks range from secure communication to distributed quantum sensing to cloud quantum computing. The secure communication leveraged quantum key distribution and potentially quantum encryption schemes. The distributed sensing used shared entanglement to enhance measurement precision beyond classical limits. The cloud quantum computing could distribute problems across networked quantum processors, though the challenge of minimizing classical communication in hybrid approaches remained. The standardization efforts for quantum networking addressed protocols, interfaces, and performance metrics. The protocols specified how entanglement distribution, quantum teleportation, or quantum key exchange should proceed. The interfaces defined how different quantum network components should interoperate. The metrics characterized network performance, secret key rate, entanglement fidelity, end-to-end latency. Standards enabled multi-vendor networks and allowed meaningful performance comparisons. The testbeds and prototype networks demonstrated quantum networking concepts at limited scale, identifying practical challenges and refining technologies. Metropolitan-scale networks connected buildings within cities, demonstrating quantum key distribution and entanglement distribution. Longer-range demonstrations used satellites or dedicated fiber links. Each prototype revealed engineering obstacles, informed next-generation designs, built expertise in operating quantum network infrastructure. The timeline for practical quantum networks remained uncertain, dependent on solving numerous technical challenges. Quantum repeaters needed improvement in efficiency and reliability. Quantum memories needed longer storage times with better fidelity. Modality conversions needed higher efficiency. The integration of components into robust systems needed engineering development. Progress continued across multiple fronts, but predicting when capabilities would mature into deployable infrastructure required acknowledging substantial remaining uncertainties. The question of whether quantum computers truly computed differently or merely executed the same logical operations through different physical mechanisms touched fundamental issues in the philosophy of computation. At one level, computation was simply transformation of inputs to outputs according to specified rules, substrate, independent. Classical computers, quantum computers, mechanical calculators, even humans with paper and pencil could all implement the same algorithms, produce identical results. The differences were in efficiency, speed, energy consumption, not in the essential nature of what was being computed. Yet, quantum computation introduced phenomena with no classical analog. Superposition wasn't simply parallel processing in the classical sense, though it enabled certain forms of parallelism. A quantum computer operating on a superposition of all possible inputs to a function didn't produce all possible outputs in any directly accessible sense. Instead, the superposition of outputs existed briefly before measurement collapsed it to a single result. The utility came from arranging interference, such that wrong answers cancelled while correct answers amplified, a distinctly quantum resource. Entanglement created correlations that violated classical intuitions about local realism. The idea that objects have definite properties independent of measurement and that influences propagate at finite speeds. Entangled qubits, separated by any distance, exhibited correlations stronger than any classical hidden variable theory could explain. Operations on entangled systems required treating them as unified wholes, not reducible to independent parts. This non-locality was purely quantum, enabling computational primitives impossible classically. The measurement problem in quantum mechanics, unresolved despite decades of debate, became practically relevant in quantum computing. Measurement collapsed superpositions to definite states, extracting classical information from quantum systems. But what constituted measurement? When exactly did collapse occur? Different interpretations of quantum mechanics gave different answers, yet quantum computers worked regardless of which interpretation one preferred. The philosophical questions didn't prevent practical implementation, though they left conceptual foundations uncertain. The reversibility of quantum gates contrasted with the irreversibility typical of classical computation. Classical operations often destroyed information. An AND gate with two inputs and one output couldn't be uniquely reversed. Quantum gates had to be reversible to preserve quantum information, implemented as unitary transformations. This requirement shaped how quantum algorithms were structured, forcing careful treatment of information flow, making explicit what classical algorithms could hide through irreversible operations. The nature of quantum randomness differed philosophically from classical randomness. Classical randomness typically reflected ignorance, deterministic processes that appeared random because we lacked complete information. Quantum randomness seemed fundamental. Measurement outcomes genuinely indeterminate until observation occurred. Whether this represented true indeterminacy or merely deeper hidden variables we couldn't access remained debated, but quantum computing relied on this apparent intrinsic randomness. The question of what problems quantum computers could solve efficiently remained partially open. Certain problems had known quantum algorithms offering speedups, sometimes exponential. But which problems admitted efficient quantum algorithms and which didn't? The relationship between classical and quantum complexity classes was understood partially, with conjectures but not proofs about inclusions and separations. The philosophical question of whether quantum mechanics granted fundamentally new computational capabilities or merely rearranged known capabilities lacked definitive answer. The simulation hypothesis, the idea that our reality might be a computational simulation, faced quantum mechanical challenges. Simulating quantum systems on classical computers scaled exponentially poorly with system size, suggesting that if reality were a simulation, it would need to be quantum. But could a quantum computer efficiently simulate quantum physics? For specific models, yes, suggesting a form of closure. Quantum systems could simulate quantum systems efficiently. Whether this extended to all physics remained uncertain. The implications of quantum computing for consciousness and the mind-body problem were speculative but intriguing. If quantum coherence played roles in biological processes, particularly in neurons, might consciousness involve quantum phenomena? Quantum computers demonstrated that quantum effects could produce behaviors difficult to explain classically. Did similar effects in the brain contribute to subjective experience? Or was this overreaching, seeing quantum mechanics where classical processes sufficed? The questions exceeded current evidence but stimulated investigation. The debate over whether quantum computers truly computed or merely exploited physical processes to solve problems revealed tensions in how we conceived computation. Was computation an abstract process instantiated in physical systems? Or was it fundamentally physical, different substrates producing genuinely different computational capabilities? Quantum computing suggested the latter, that physics constrained and enabled computation in ways that abstract models alone couldn't capture. The role of the observer in quantum mechanics became practically relevant in quantum computing. Measurement required classical apparatus, observers external to the quantum system. But where exactly was the boundary between quantum and classical? Could quantum computers grow large enough that treating them as purely quantum became untenable? These questions weren't just philosophical, but practical for understanding limits to scalability and decoherence. The relationship between information and physical reality took new forms in quantum computing. Information wasn't just abstract patterns, but physical quantities subject to quantum mechanical laws. The no-cloning theorem prohibited copying arbitrary quantum states, information fundamentally limited by physics. The entanglement entropy quantified quantum correlations, information distributed non-locally across entangled systems. Information became a physical resource, created, manipulated, consumed in quantum computations. The thermodynamics of computation, the relationship between information processing and energy dissipation, manifested differently in quantum systems. Landauer's principle stated that erasing information required minimum energy dissipation, linking information to thermodynamics. Reversible quantum gates that preserved information could, in principle, operate without dissipating energy, though practical implementations always lost some energy to decoherence and control. The theoretical limits and practical realities diverged, but both shaped how we understood quantum computation's physical costs. The emergence of classical behavior from quantum mechanics, decoherence transforming superpositions into classical probability distributions, became visible in quantum computers as systems scaled. Small systems exhibited purely quantum behavior, superpositions and entanglement dominating. larger systems coupled more strongly to environments, decoherence, destroying quantum properties. The transition wasn't sharp, but gradual. Quantum computers operating in a regime where both quantum and classical aspects were relevant. The limits of knowledge accessible through quantum computation raised epistemological questions. Some information about quantum states was fundamentally inaccessible through measurement, hidden in phases or in correlations that observation destroyed. Quantum tomography could reconstruct states through many measurements on identical copies, but single-shot measurement extracted limited information. This irreducible uncertainty wasn't merely practical, but fundamental. Quantum mechanics limiting what could be known. The verification of quantum computations presented both practical and philosophical challenges. How could you verify that a quantum computer produced the correct answer if you couldn't efficiently check it classically? For problems where quantum speedup existed precisely because classical verification was hard, trusting quantum results required either indirect validation or accepting results on faith. The philosophical tension between verification and efficiency shaped discussions of quantum advantage. The determinism versus indeterminism debate found new context in quantum computing. The quantum state evolved deterministically according to Schrödinger's equation between measurements, but measurement introduced apparent indeterminism. Whether this reflected genuine randomness or incomplete description remained contested. Quantum computing worked identically under either interpretation, suggesting the philosophical question might be empirically undecidable. The role of time in quantum mechanics, already puzzling in standard quantum theory, became practically relevant in quantum computing. Quantum gates were time reversible. Computation could proceed forward or backward in time mathematically, but measurement introduced time asymmetry, collapsing superpositions irreversibly. The arrow of time emerged from decoherence and thermodynamics, not from quantum mechanics itself. Quantum computers embodied this tension between reversible evolution and irreversible observation. The implications for free will, if any, from quantum randomness remained as unclear as they'd always been. True randomness in measurement outcomes didn't obviously enable free will any more than determinism precluded it. Quantum computers demonstrated that quantum mechanics could influence macroscopic outcomes, measurement results determined by quantum uncertainty. But whether this had implications for consciousness or agency exceeded what the technology revealed. The computational theory of mind, the idea that thinking was a form of computation, faced both support and challenge from quantum computing. If minds were computational, could they be quantum computational? Did the brain exploit quantum effects? Or did decoherence restrict neural processes to classical computation? The questions remained open, evidence limited, implications uncertain. Quantum computers showed that quantum computation was possible in principle, but didn't demonstrate its necessity for intelligence. The ontological status of the quantum state, whether it represented reality or merely our knowledge of reality, remained debated. Quantum computers operated identically under either interpretation. Whether the superposition before measurement was real or just described what we knew made no practical difference to implementing algorithms or interpreting results. The philosophical question persisted without affecting engineering. The relationship between mathematics and physical reality found new expression in quantum computing. Mathematical structures like Hilbert spaces and unitary operators directly corresponded to physical quantum states and operations. The unreasonable effectiveness of mathematics in physics manifested in quantum computing's ability to translate abstract mathematical operations into physical processes that produce desired computational results. The limits of reductionism appeared in quantum computing's emergent properties. Understanding individual qubits didn't automatically confer understanding of large entangled systems. The whole exceeded the sum of its parts in ways that resisted decomposition. This holism was characteristic of quantum mechanics generally, but became practically important in quantum computing, where the interesting behavior emerged from complex, entangled states not reducible to individual qubit descriptions. The trajectory of quantum computing suggested multiple possible futures, each contingent on solving different technical challenges and achieving various milestones. The path toward fault-tolerant quantum computers capable of running arbitrary algorithms indefinitely required demonstrating quantum error correction at scale, maintaining logical qubit error rates below physical rates, scaling to thousands or millions of physical qubits. The technical barriers remained substantial, but progress continued across multiple fronts, each advance narrowing the gap between current capabilities and fault-tolerant operation. The error correction threshold represented a critical boundary, the point where adding more qubits to error correction codes actually reduced logical error rates, rather than simply accumulating more physical errors. Experiments had demonstrated basic error correction, but achieving true threshold behavior required better physical qubits, more sophisticated codes, faster error detection and correction cycles. The theoretical understanding was solid. The engineering challenge was implementation at sufficient scale and fidelity. The alternative path emphasized near-term applications using noisy intermediate-scale quantum devices, accepting that error correction remained out of reach and instead focusing on problems where approximate answers had value. Variational algorithms, error mitigation techniques, and hybrid quantum classical approaches might provide useful results despite imperfect qubits. The strategy acknowledged current limitations while extracting whatever value was accessible, hoping that accumulated experience would inform longer-term development. The diversification of quantum computing approaches meant that different physical platforms might excel at different applications. Superconducting systems might suit problems requiring fast gates and programmable connectivity. Ion traps might excel where long coherence times mattered more than speed. Photonic systems might enable quantum networking and distributed quantum computing. Neutral atoms might offer unique capabilities for quantum simulation. The future might be heterogeneous rather than converging on a single dominant technology. The integration of quantum accelerators into classical computing infrastructure paralleled how graphics processors became standard components for machine learning and scientific computing. Quantum processors might become specialized accelerators called for specific subroutines, the bulk of computation remaining classical, but benefiting from quantum speedup on targeted operations. This hybrid approach seemed more plausible near-term than standalone quantum computers replacing classical systems. The application domains most likely to benefit from quantum computing remained partially speculative. Quantum chemistry and materials simulation had strong theoretical foundations for quantum advantage. The problems naturally quantum mechanical. Optimization and machine learning showed promise, but required further algorithm development and hardware improvement to demonstrate clear benefits. Cryptography faced certain disruption if large-scale quantum computers materialized, driving defensive preparations even without knowing the timeline. The timeline uncertainties complicated planning and investment decisions. Optimists projected fault-tolerant quantum computers within a decade or two. Pessimists warned that fundamental obstacles might emerge, that scaling challenges might prove insurmountable, that useful quantum advantage might remain elusive indefinitely. The truth likely lay between extremes, progress continuing, but punctuated by unexpected difficulties and surprising breakthroughs, the path non-linear and unpredictable. The workforce requirements for a mature quantum computing industry would span multiple disciplines and skill levels. Quantum hardware engineers would design and build quantum processors. Cryogenic engineers would develop better refrigeration and control systems. Quantum algorithm researchers would discover new applications and speed-ups. Software engineers would build tools and infrastructure. Domain scientists would apply quantum computing to their fields. Technicians would operate and maintain systems. The educational pipeline needed expansion to meet anticipated demand. The standardization efforts would intensify as the field matured, establishing benchmarks, protocols, and interfaces that enabled interoperability and fair comparison. The standards would need to balance flexibility for innovation against stability for deployment. Premature standardization could lock in suboptimal approaches, but excessive fragmentation would impede adoption and create barriers to entry. The timing and scope of standardization would shape the industry's evolution. The economic models for quantum computing would evolve from research funding and venture capital towards sustainable business models. The revenue sources might include cloud computing services, specialized consulting, licensing of intellectual property, integration into existing products and services. The cost structure would shift from dominated by research and development toward manufacturing, operations, and support. The The transition from subsidized research to profitable business would test the technology's practical value. The geopolitical implications of quantum computing capabilities would drive national investments and international competition. Countries would seek quantum computing expertise, manufacturing capacity, and application capabilities, viewing the technology as strategically important. The competition might spur faster progress through increased resources, or it might fragment the field through restricted collaboration. Export controls, technology transfer restrictions, and national security concerns would shape what information and technology flowed across borders. The environmental considerations would grow in importance as quantum computing scaled. The energy consumption of dilution refrigerators, control electronics, and classical computing infrastructure represented significant power draw. More efficient refrigeration, optimized control, and better algorithms could reduce energy per computation, but growing deployment might still increase total consumption. The life cycle impacts of manufacturing, operation, and disposal would require attention as quantum computing transitioned from research prototypes to infrastructure. The convergence of quantum computing with other emerging technologies might produce capabilities exceeding what either enabled alone. Quantum computing, combined with advanced classical machine learning, could tackle optimization problems beyond either approach separately. Quantum sensors feeding data to quantum processors might enable new measurement capabilities. Quantum communication networks connecting quantum computers might enable distributed quantum algorithms. The intersections remained largely unexplored, but suggested rich possibilities. The philosophical implications of practical quantum computing would deepen as the technology matured. Demonstrating quantum advantage on problems of practical significance would force reckoning with quantum mechanics implications for computation, information, and physical reality. The transition from laboratory curiosities to tools shaping society would make quantum mechanics' strange predictions tangibly relevant to everyday life in new ways. The societal impacts of quantum computing remain difficult to predict, dependent on which applications materialized and how widely they deployed. Breaking current encryption would disrupt cybersecurity, requiring wholesale transition to quantum-resistant alternatives. Accelerating drug discovery could improve healthcare. Optimizing logistics could reduce waste and energy consumption. Designing better materials could enable new technologies, but the impacts depended on achieving sufficient quantum advantage to matter practically, a threshold not yet clearly crossed. The education and public understanding of quantum computing faced challenges from the subject's inherent difficulty. Quantum mechanics defied classical intuition, required mathematical sophistication to describe precisely, resisted simple explanations. Yet public understanding mattered for informed policy decisions, workforce development, and realistic expectations about capabilities and limitations. The communication challenge was finding ways to convey essential ideas without oversimplifying to the point of distortion. The long-term vision for quantum computing extended beyond current engineering challenges to more speculative possibilities. Room temperature quantum computers would eliminate cryogenic infrastructure requirements, though no clear path existed to maintaining quantum coherence without extreme cold. Topological quantum computers using exotic states of matter might offer inherent error protection, though experimental demonstration remained elusive. Quantum computers based on entirely different physical principles might emerge from current research into quantum materials and phenomena. The ultimate limits of quantum computing remained uncertain. Quantum mechanics imposed fundamental constraints on what could be computed efficiently, problems in certain complexity classes remaining hard even for quantum computers. But the boundaries of those complexity classes weren't fully mapped, leaving open whether problems currently believed hard might admit quantum algorithms not yet discovered. The theoretical understanding would deepen as the field matured. The coexistence of classical and quantum computing seemed assured, regardless of quantum computing's ultimate capabilities. Even if quantum computers achieved dramatic speedups for certain problems, classical computers would remain superior for many tasks, cheaper for simple computations, more practical for general-purpose computing. The future likely involved heterogeneous systems using each type of computer for what it did best, not wholesale replacement of one by the other. The journey from teaching sand to think had led to teaching vacuum, superconducting circuits, and trapped atoms to exploit quantum mechanics for computation. The progression from classical to quantum represented not just a technological evolution, but a philosophical one, forcing engagement with nature's deepest puzzles while pursuing practical capabilities. The quantum computers built thus far were primitive by the standards of what might eventually be possible, but they already represented achievements remarkable for how they harnessed quantum phenomena that seemed impossibly delicate for useful application. The story remained unfinished, the technology still emerging, the capabilities still developing. What quantum computing would ultimately achieve, which problems it would solve, how widely it would deploy, what impacts it would have, all remained uncertain, dependent on solving challenges both foreseen and unexpected. The work continued in laboratories and facilities around the world. Researchers and engineers pushing against the boundaries of what quantum systems could do. Each advance expanding understanding while revealing new questions. The subatomic frontier into which quantum computing ventured offered both promise and mystery. Promise of computational capabilities impossible classically, solving problems that mattered for science, technology, and society. Mystery in the quantum mechanical principles underlying the technology, phenomena we could harness without fully understanding, effects we could predict mathematically but struggled to explain intuitively. The journey continued, quantum computing advancing from theoretical speculation toward practical reality, exploring what became possible when we learned to compute with nature's deepest principles. Thank you for spending this time exploring the quantum frontier, where the boundaries between the possible and impossible continue to shift. If you found value in this journey through the microscopic details of quantum computing's development, consider sharing it with others who appreciate the patient accumulation of understanding. Remember, the most profound technologies emerge not from sudden breakthroughs, but from sustained attention to detail, from countless small refinements, from the quiet persistence of those willing to work at the edge of what's known. Sleep well, knowing that somewhere qubits exist in superposition, waiting for measurement to collapse their infinite possibilities into singular truths. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.